Hello, good evening, everyone. Uh, I am Prof.Anwarul Siddiqui. Today, I am going to conduct a lecture, basically a GATE lecture under Prerna scheme for the subject Computer Architecture and Organization. Computer architecture and organization is a very important subject because its weightage is of 8 to 11 marks in GATE, and every year some 8 to 11 mark questions from this particular subject comes in the GATE. So this subject is quite easy to understand. The syllabus is also not very vast, and if you prepare this subject well, there are good chances that you will score 8 to 11 marks from this subject under GATE. Okay, so we will start our lecture today with von Neumann architecture, or by learning what are the basic functional units of a computer. So as you can see on the screen, that I have drawn a diagram which indicates what are the basic functional units of a computer. So from this diagram, it is clearly visible that there are three particular components. One is IO. IO part consists of input and output devices. Then there is something called as memory, and there is a processor. Processor consists of arithmetic and logic unit and control unit. So we'll not go into very deep about these functional units. We'll just see broadly that what is the role and responsibility of each of these functional units. Let us start with memory unit. Memory is a very important component of any computer. What is the role of memory? Role of memory is to store programs and data. Okay, there are two classes of memory. Basically, there is a memory hierarchy which is associated with each and every computer, and we are going to learn more about memory in details when we are going to cover the memory topic, or memory lecture on memory. But basically, broadly, memory is divided into two classes. One is primary storage memory. Primary storage consists of RAM. uh, Primary storage is a fast memory. All the programs are executed in the primary memory. So basically, the program that are stored in the primary memory can only be executed. The program that are stored in the secondary memory has to be brought into primary memory first, and then only these programs can be executed. Okay, and example of primary memory is RAM. Okay, cache memory is also present in the memory hierarchy, and we'll learn about cache memory when we are going to study memory in details. Some of the other important attributes of primary memory is that primary memory is faster, and it is a bit costlier, and it is normally small in size. Then there is a secondary storage. Secondary storage is a very large memory which can store all the data. It is normally, the size of secondary memory is in GBs, TBs, and it is comparatively cheaper as compared to primary memory. And there is arithmetic and logical units. So as all of you must be knowing, that arithmetic and logical unit is basically responsible for performing all the mathematical and logical operations. So basically, whenever we need to perform any mathematical or logical operations, so that operations are carried out basically in the arithmetic and logic unit. Okay, we are not going to go into very deep about what is ALU, because most of us are already know what is ALU. This is something important, and this is something we must know, that what is a control unit. Okay, so basically all the operations of the computers are controlled by the control unit. What is the role and responsibility of control unit? Control unit governs all the input output operations that are being carried out in the computer. Control unit basically generate all the control signals that are necessary for execution of a computer, execution of a instruction. So basically, unless and until control unit does not generate control signals, the execution of operation, the execution of instruction cannot be performed. What is a prime, or some example of control functions? that is controlled by control unit. So basically read and write are control functions that are generated by control unit. So what is a read operation? Basically whenever a control unit give a read operation, the data from memory gets transferred into the processor. What is a write operation? Whenever a control unit gives a write control signal, the data which whatever data is present in the control unit, it is again transferred back to the memory. So we'll learn about control unit in detail as we go forward. Okay, this is a very important diagram which is showing the connection between the processor and the memory. Okay, so basically the processor is connected with the memory through three buses. What are the name of these buses? First bus is called as address bus, second bus is called as data bus, and third is called as control bus. What is the role of address bus? The address bus carries the address. What is the role of data bus? The data bus transfers data to and from memory. Okay, so data can be brought from memory to the processor, and data can also be transferred from the processor to the memory. So as you can see in this particular diagram, the memory is connected with the MDR. MDR stands for memory data register. Okay, so memory data register is connected with the memory through a bidirectional arrow. What does this bidirectional arrow indicates? That the data from memory can be brought into the processor, and the data from processor can be stored back into the memory. As you can see that MAR is connected to the memory through a unidirectional arrow. What does this specify? This specify that the processor generates the address, and that address is specified, or that address is specified to the memory through this address bus. So memory cannot generate its own address. Address is always generated by the processor and specified to the memory. Therefore MAR is connected to the memory through a unidirectional, and the direction is from processor to the memory. Okay, then there is something called as control bus, which carries control signals. I have given just some time before, I have given the examples of control signal. What are control signals? Some of the control signals are read and write. Okay, so when we see here in the diagram, the memory is also connected to the control unit in a bidirectional way. What does it means? That control signals are sent from processor to the memory, and memory can also send some control signals to the processor. This basically is the indication that when a read or write request is generated. Okay, so memory specifies to the processor that whether the read or write operation is completed or not, because the processor is very fast and the memory is very slow as compared to the processor. So basically processor initiates the read and write operation and then goes back and do its own work. So memory specifies the processor that whatever read or write request was carried out or started by the processor, whether it is completed or not. Okay, so that is why we can see that control unit is connected to the memory through bidirectional arrow. And there are some important components that are shown in this diagram. One is program counter. Program counter is the most important register in the processor. What is the role of program counter? Program counter keeps the track of current instruction being executed by the processor. So basically if we are going to execute a program which is consisting of 10 lines, so the execution of program cannot be started unless and until the address of first line, okay, the first line of the program is not present in the program counter. So when the address of first line of the program is present in the program counter, then the processor can start executing the program. Okay, this program counter transfer it address in the MAR. Then MAR specifies that address to the memory, and while that instruction is being carried out, the contents of the program counter is auto incremented to specify or to indicate the address of the next instruction that needs to be executed. So program counter, this is the main or basic difference between memory address register and program counter. Okay, so basically program counter will always specify the address of the instruction which is going to be executed next, and MAR will always contain the address of the instruction which is currently being executed. This thing is very important, and it must be very, very, very clear. Then there is something called as instruction register. What is the instruction register? Whatever instructions are brought from memory to the processor, it is stored in a register which is known as instruction register. Okay, so whenever we fetch any instruction from the memory to the processor, that instruction is forwarded in the instruction register where it is decoded, and then remaining execution process takes place within the processor. Then there are a set of general purpose registers that are present within the processor. These general purpose registers are numbered from R0 to Rn minus 1. Basically, there are n general purpose registers that are present in the CPU or processor. These general purpose registers are basically used for storing the intermediate results that are generated within or while doing or performing some mathematical operations. So basically, these general purpose registers can also be used by the programmer in their programs. These general purpose registers are capable of holding only one word of information, or they can store only one. Basically, if we can say, yes, there's general purpose registers are very small and they can hold only one word of information. Okay, the size of word depends from machine to machine. Okay, if some machine is having the word size as 8 bits or 1 byte, then this general purpose register will be able to hold 8 bits of information. If a machine is of 16-bit words, then the size of this general purpose register will be 16 bits or 32 bits or 64 bits, depending upon whatever the size of word is supported by the machine. Then what is ALU? We have already studied. ALU is basically the arithmetic and logic unit, which is used for performing all the mathematical and logical operations. Okay, these are the registers that are present in the instruction, that are present in the processor. We have already discussed about these registers: IR, program counter, general purpose registers, R0 to Rn minus 1, memory address register, and memory data register. What are the operating steps? Uh, Basically, these operating steps are indicating that, suppose if you want to execute any program, or even if you want to execute a single instruction, then these are the steps that needs to be performed. So we all know that before the execution of program starts, or if you want to execute even a single line of program, that program is sorry, this program is stored in the main memory or RAM. So what is the first thing? The first thing is we need to bring that program from the memory into the processor. Okay, so how can we do that? For that, we need to send the address of that particular instruction in the program counter. So program counter is basically set to point the first instruction that needs to be executed. Okay, then the contents of program counter are transferred to MAR. Whatever address is there in the whatever address is present in the program counter, it is transferred to the memory address register. Okay, and then a read signal is sent to the memory. So read signal is basically a control signal that is sent to the memory. What does read signal specify? Read signal specify that the data from the memory has to be brought into the processor. That is what read signals specify. Okay, okay, when read signal is issued, the instruction is loaded into the MDR. So if you go back to this diagram, you can see that memory is connected to the processor through MDR. So whatever data is transferred from the memory to the processor, or from the processor to the memory, can only be transferred through memory data register. Okay, so whenever any data from memory comes, whether it is a instruction or whether it is a variable, okay, any data from memory will first come into MDR, and then from MDR, depending upon whether it is a instruction or it is a variable or value data, it will be decided that where that data will be transferred. So if it is an instruction, okay, it will be transferred into IR, instruction register, and if it is data, operand, values, then it will be transferred to the either general purpose registers or ALU, depending upon whatever is specified in the instruction. Okay, so this is very important thing that each of you must know, that memory is connected to the processor through three special registers: MAR, MDR, and control. So MAR will specify the address to the memory. Whatever data is transferred, that data transfer takes place through MDR only, and control unit generates or gives the control signal to the memory. Okay, we'll come back to this slide. Then instruction is loaded into MDR. Okay, and then since it is an instruction, okay, as I have already specified, this instruction will be transferred where? This instruction will be transferred to instruction register. Okay, after the instruction is transferred to the instruction register, these instruction needs to be decoded. What do we mean by decoding? Okay, decoding means every instruction consists of two parts. Every instruction consists of two parts. Those two parts are opcode and operand. What is a opcode? Opcode specifies the operation that needs to be executed, and operand specifies that these operation will be carried out on which values. For example, suppose you are writing a instruction add a comma b. So these add a comma b here in this particular instruction, add is the opcode because it is specifying the operation. What is the operation here? Addition operation. That this instruction is telling to perform addition operation. Okay, now if you want to add, you need basically or minimum two numbers. Okay, so what are the two numbers? These two numbers are present at memory location A and B. So basically A and B are called as operands because they are specifying, or they are holding the values upon which addition operation will be performed. Okay, so decoding an instruction means finding out what is the opcode which is specified in the instruction, and then where are the values or operands present so that those operands can be fetched into the processor. This is what decoding means. After the operands are fetched from the memory or wherever they are present to the ALU, we will execute the instruction. After the execution of instruction is completed, the last step is to store the result into the memory or whatever address is specified in the instruction. That is called as write operation or store operation. Okay, so whenever we perform the write operation and store operation, then that particular execution of an instruction is completed. Uh, these are again continuation of the previous slide. Operands can be present in general purpose registers, like I previously told you that general purpose registers can be used by a programmer, okay, in his program. So these general purpose registers can also be used to hold the values that are being specified in the instruction, and the operand can also be a memory address. Okay, so if it is a memory address, the address is specified in the instruction, then we go to that particular address and we fetch the values from that particular address to the ALU, and then we perform the particular operation. Okay, then storing the result back, I have already told you that the result can be stored either in the general purpose registers or in the memory. Whatever address is specified in the instruction, we will store the result there. If it is the general purpose registers, then the result will be stored in the general purpose register. If it is a memory address, then we will go to that particular memory address and we will store the result. Okay, and this thing also has been specified by me that whenever while the first instruction is being executed, okay, the value or contents of the program counter is auto incremented to point to the next instruction, so that as soon as the execution of first instruction completes, the execution of second instruction can be started. Okay, so these are the steps for executing a single instruction. Now, why I'm giving this so much focus on these steps? Because in future when we are going to study pipelining, then these are the steps, okay, of pipelining. So there we will not have to spend much time if we are understanding these things now. So basically, executing a instruction can be carried out into 4 or 5 steps, sometimes 4, sometimes 5, depending upon whether we are merging some steps or not. Okay, so first step for executing any instruction is always and always fetch the instruction, because unless and until the instruction is brought into the processor, it cannot be executed. So before the execution of any instruction starts, that instruction will always be present in the memory. Okay, and we have to fetch that instruction from the memory to the processor to be able to execute that instruction. So what is this step called? This step is called as fetch the instruction, and we can simply denote it by a capital alphabet F. Okay, then second step is always decode. What do we mean by decode? Decode specifies that what is the opcode and operation, or basically what is mentioned in the instruction, what do the processor needs to do, what is this instruction specifying or telling the processor to do. So basically, you find out the opcode, what is the operation specified in the instruction. Then you try to find out where are the operands present, whether they are present in the general purpose register or they are present in the memory addresses. Okay, and then what do we do? Once we know the address of the operands, then we go to that particular memory location or what that particular general purpose register, then we fetch that operand and bring it back to the ALU. After all the operands are present or all the values have been fetched to in the ALU, we can now execute the instruction. So next step, or step number 4, is executing the instruction. Okay, and then finally when the execution is over, the result has been generated. That result is generated by ALU. That result needs to be stored at the destination. So whatever destination is specified in the instruction, we need to store that particular result at that location. The location of result could be general purpose registers, or it could be a memory location also. Here I have tried to give some example of opcode and operands. Okay, so like I've specified previously, that all the instruction consist of opcode. Opcode are addition, subtraction, multiplications, etc. So these are basically sorry. So what is these things specifying? These things are specifying that what is the operation that needs to be performed. Okay, so if you are writing add a comma b, that means you are specifying that you need to perform the addition operation. Suppose you write sub a comma b, that means you are specifying that you need to perform subtraction. If you are writing mul a comma b, then you are specifying that you have to multiply two values. Okay, and what is the operand? These are the values, okay, upon which the operation needs to be performed. So you can write add a comma b. A and b are the address where the values are stored. It could be direct values also. You can also write something in higher level languages, add 2 plus 3, or you can directly write a equal to 2 plus 3. Okay, so in here you are directly specifying the values upon which operation needs to be performed. That is also possible, that is also allowed some higher in some higher level uh, programming languages. Then there is something called as location. If you can specify the location that where the data needs to be moved. Okay, so these are all examples of operand. Okay, now there is a very important concept, that what are the instruction formats. Okay, instruction formats. So basically there are four type of instructions that are supported by any particular machine. First type of instruction is three address instruction. Here I have tried to give an example: add R2, R3, R1. Okay, so why it is called as three address instruction? Because in this particular instruction, we have specified the address of three operands or three variables. Okay, so if any instruction specifies, or if any machine support instructions that can specify maximum three variables or operands, are called as three address instructions. And what is the example? Add r2 comma r3 comma r1. We are going to see an example that what is the difference between three address instructions, what is the difference between two address instructions, what is a one address instruction, what is a zero address instruction. Okay, all these things we are going to see. Then there is something called as two address instruction. What is two address instructions? If in any instruction, or if any particular machine allows that maximum two address can be specified in any particular instruction, then that is called as two address instructions. So here add r2 comma r1, we have specified two addresses in this particular instruction. What are those two addresses? R1 and R2. In the above example, in three address instruction, we have specified R1, R2, and R3. Okay, and then there is something called as one address instruction. In this, we are specifying only address of one variable. Okay, then you can say that it is not possible. How can it be possible that we can add only one? That we can add only one variable? It is not possible, because addition is possible if and only if there are two variables. So from where does the second variable comes? Okay, so if the machine is supporting one address instructions, then always and always the second variable will be fetched from the accumulator. Okay, so what happens in one address instructions? In one address instructions, the address of one variable is specified in the instruction, and the other variable is by default present in the accumulator. The value of other operand is fetched from the accumulator, as you can see in the example also. As you can see in the example also, that one variable is m. Okay, so we are fetching the value of m, and then other variable, the value of other variable, we are fetching from accumulator. Okay. Then one very important thing I forgot to mention, that these instructions also specify a very important thing, that uh, they specify the source and destination also. So normally whenever we write any instruction, okay, so that instruction is read as source and destination. So first, whatever is variable it is specified first, normally that is the source, and the variable specified in the last is both, it is the source also and it is the destination also. Okay, so let us consider this particular example. Okay, add r2 comma r1. So these instruction can also be read as add source comma destination. Okay, so r2 and r1, these are the source from where the values will be fetched for performing addition. Okay, now one must wonder that, okay, if both are source, then where the values will be stored, or after performing the addition of values from r1 and r2, where will be the result stored? Okay, so by default the result will be stored in the r1, because r1 is also acting as a destination. So as you can see on the right, when we are performing the addition operation, okay, so we are fetching the values of variables from r1 register, we are fetching the values from r2 register to the ALU, then we perform the operation, addition operation, and the result is stored back in the r1 register. Okay, so r1 is the destination also. Here also you can see r1 is specified in the last, so it is also read as source comma destination. So r2 and r3, these are the source, and then r1 is the destination. So values from r1, r2, and r3 are fetched, and the addition is performed, and the result is stored in the r1 register. Here we have only specified one variable, address of only one variable. So what will happen? This variable, this variable is considered as source. Okay, and accumulator will be the destination. So you can see what is happening here. One value is fetched from memory location M, the other value is fetched from accumulator, and when the addition operation is performed, the result is stored at the accumulator. Okay, so these are very important and basic concepts that one needs to understand in order to understand the higher concepts. Okay, so this is how one address instructions are executed. And there is something called as zero address instructions. As you can see here, that we have not specified the address of any variables, we have just given a single command. What we have given, add. So it is clear from the instruction that we need to perform addition operation, but for performing addition operation we need two values. Where are those two values? It is not specified in the instruction. So how are we going to fetch these two values? Okay, so these two values will be fetched from the stack. Normally, zero address instructions are supported by the machines which support the memory, which is organized in the form of stack. Okay, so by default, whatever data is present in the memory, that data will be stored or organized in the form of stack. Okay, what is a stack? Everyone is knowing that we are normally, it is a shelf like structure where we are continuously pushing and popping the data. So basically when we want to store a data in a stack, so this that operation is called as push, and whenever we want to fetch a data from a stack, that operation is called as pop. Okay, so how these addition operation will be performed? The first value will be fetched from top of stack, then second value will be fetched from top of stack minus 1, means second location. These two values will be added, and the result will be stored at the top of the stack. Okay, this is how zero address instructions are executed. Let's move forward. Now these are some important thing. These are these thing we need to understand, because normally so many questions come from this particular topic, that you have been given a instruction. Okay, and then they ask you that suppose you need to execute this instruction by three address instruction format machine, by two address instruction format machine, one address or zero address. Okay, so we'll take this one particular example where you are given an instruction. What is the instruction? It is a mathematical equation, a plus b multiplied by c plus d. This is a mathematical equation, and we need to execute this particular instruction by all the four instruction formats. So one by one we will see that how can this instruction be executed by using all the four instruction formats. So first we will see how we will execute this instruction if we are having a three address instruction machine. So as we all know that in three address instruction machine, we can specify three addresses in our instruction. Okay, so how the execution will proceed? The first instruction internally will be executed as add a comma b comma r1. Now if you remember, these r1 are general purpose registers which are used to store the intermediate results. Okay, so a plus b, addition of a plus b will generate an intermediate result which will be required in the future for executing this complete instruction. So therefore we can use the general purpose register r1 to store the value of addition of a plus b, so that we can use it in the future. Okay, so what is the internal execution here? Add a comma b comma r1. Okay, and then again I have specified that whatever variable is specified in the last, it will work as the destination, and the variables that are specified at the beginning will be considered as the source. So a and b will act as source from where the data will be fetched, and r1 is the destination where the result of addition of a and b is going to be stored. Okay, so I think this needs to be very clear to all of you. Okay, and then here I am also specifying that what is actually happening. These a and b are the address of memory locations. That is why we have written here ma and mb to specify that it is a memory location. So from memory location a we will fetch one value, from memory location b we will fetch one value. Both these values are fetched into the ALU, then addition operation is performed, and the result is transferred or stored temporarily in the R1 register, general purpose register R1. Okay, so addition of A plus B is completed. Then what is the second step? You need to add C plus D. So what is the second step of execution? Add c comma d comma r2. Again c and d is specified in the instruction, but r2 we are using to hold the result of addition of c and d. Again it is a general purpose register which can store the result of addition of c and d. So here r2 register will store the value of addition of c and d. Okay, okay. Then finally the we have the result of additions of a plus b and c plus d. So then third step could be that r1 r2 we are giving a multiply command here. R1 r2 means the value which whatever value is stored in the r1 will be multiplied by r2, and then result is stored in the memory location x. So this thing is specified here. R1 is a general purpose register, R2 is a general purpose register. They are holding the value of A plus B and C plus D. Then these two values is multiplied, and then the result is stored in the memory location X. Okay. So as you can see here that in order to execute the instruction A plus B multiplied by C plus D, if we are having three address instructions, this particular task can be completed in three steps or in three instructions only. Okay, but if we are having two address format, okay, now let us try to see that if our machine is having or supporting two address format, then how many steps or how many instructions are we going to require in order to perform the same task, that is a plus b multiplied by c plus d. Okay, let us see. Now two address format. Okay, so how it will be done? What is the first thing we have written? Move a comma r1. So when we are writing move a comma r1, basically we are transferring the content of memory location a to the register r1. Okay, now what is the second step? In the second step we are adding b comma r1. Okay, so the result is going to be stored in the register r1 because here r1 is acting as a destination. So r1 will hold the value of addition r1 which was already having the value from memory location a plus the value from memory location B. Now these two values are added and the result is stored in the intermediate or general purpose register R1. Okay. Then what we'll do in step number 3? Okay, so in step number 3 we will transfer the contents of C in the memory register R2. So from memory register C, from memory location C, the data is transferred into the general purpose register R2. Okay, then we will give a add command, add d comma r2. So here d is the source and r2 is the destination. So we can see here that values from r2 register and from memory location d, these two values will be added and the result will be stored in the r2 register. Okay, this thing is very clear. Now what we need to do? We need to multiply the values of r2 and r1. So next instruction will be multiply r2 comma r1, and finally whatever result is generated, because r1 is the destination, that result is initially stored in the r1, and from r1 that result needs to be stored in the memory location x. So we will transfer the contents of R1 register to the X register. Okay. So if we are having two address instruction formats, you can see the total number of instructions required or total steps for evaluating A plus B multiplied by C plus D increases from 3 to 6. In three address instruction formats, we were requiring only three instruction or three steps to evaluate the above equation. When we are having two instruction formats, we require six steps or six instruction to perform the same task. Now coming to the one address instruction. So as it is clearly visible that in one address instruction, the number of steps or number of instruction required is further increased to 7. So now we require 7 steps or 7 instruction to perform the same task. Let us try to understand how we are going to perform the same task if we are having one address instruction. Okay, so what we will do, we will give a command load A. So basically what is happening, the data from memory address A will be transferred to the accumulator. Okay, now next command will be add B. Okay, so if you can remember, when we studied one address instruction, what we studied there, that in one address instruction we always specify the address of one variable, the other variable is by default fetched from accumulator. Okay, so this thing is now very clear from this particular example what we have written, add B. Okay, so here it is clear that one variable is present in the memory location B and other variable will be fetched from accumulator, and the result of addition will also be stored in the accumulator. Okay, so let us see here what is actually happening. uh, from the memory location B, one value is fetched. From the accumulator, one value is fetched. The addition is performed in the arithmetic and logic unit, and then the result is stored back in the accumulator. Okay, then the result is now present in accumulator. We cannot leave that result here because then it will be overwritten. Okay, so what we will do, we will store that result into some temporary register. So that T could be any temporary register or memory location. Okay, so what we'll do, we'll store the value of accumulator into some temporary location. So contents of accumulator is transferred to memory location T. Then what we are specifying, load C. Okay, so when we write load C, the contents of memory location C will be stored in the accumulator. Then we are doing add D. What will happen when we give the command add D? The contents of memory location D will be added with the contents of accumulator. What is the contents of accumulator? The contents of accumulator is the content which was stored in the memory location C. So data from memory location C was always already present in the accumulator. To this data, the contents of memory location D is added and the result is stored in the accumulator. Now see what is happening. We are already having our data in memory location T. So what we need to, and accumulator is already having the data. What data accumulator is having? Accumulator is having the result of addition of C plus D. Okay, so next command that we will give is multiply T or multi. What will happen when we will specify multi? The memory, the data from memory location T, okay, will be multiplied with the contents of accumulator. What was stored at memory location T? The result of addition of A plus B. And what was stored in the accumulator? The result of addition of C plus D. So now A plus B will be multiplied by C plus D. And that result will be stored where? This result will be stored in the accumulator. Okay. So now the contents of accumulator will be transferred to the destination specified in the instruction. So like all the previous instructions, we will assume that these result needs to be stored at a memory location X. Okay, so what command we will give is store X. So what will happen, the content of the accumulator will be moved to memory location X. Okay, so this is how the same equation A plus B multiplied by C plus D will be executed if we are having one address instruction format. Okay, let us go to zero address instruction format. Suppose we are having zero address instruction format, or our machine support zero address instructions. Okay, so again it is clearly evident that the number of instructions or number of steps that are required to execute the same equation further increased from 7 to 8. Okay, so now how many steps or how many instructions that we need to write to do the same task? What is the task that we need to perform? We need to perform the addition a plus b multiplied by c plus d. This thing we need to, this equation we need to execute. Okay, so let us try to understand how it will be done by using zero address instruction format. Okay, so first of all, what we'll do, we'll give a command push a. What do we mean by push a? I have mentioned some time back that zero address instruction, the memory is organized in the form of a stack. Okay, and what are the in on stack? There are only two operations that are possible. Okay, what are those two operations that are possible on stack? Those two operations are push and pop. Okay, so whenever we give a push command, so a data or a value is stored to the top of the stack. Initially the stack is empty, so whenever we insert any data into the stack, so basically that value is stored at a location which we specify as top of the stack. So let us assume that initially the stack was empty, and when you are giving a command push a, the value the value a will be stored at the top of the stack. Okay, now what we'll do, then we will use the second command push b. Okay, so now the b will be new top of stack, and it will be pushed to the stack. Okay, so now basically what is happening, a is on the t minus 1 location and b is at the top of the stack. Okay, so next thing is we will do the add. So if you can remember, when I was teaching you zero address instruction, in the zero address instruction we are not specifying any address, or we are giving only the command such as add, sub, mul, divide. Okay, so when we are giving the add command, where are the two values coming from? The two values are coming from the top of the stack and top of the stack minus 1 location. Okay, so top of the stack currently is b, and t minus 1, top of a stack minus 1 is a, is having the value of a. Okay, so when we are doing giving the add command, so basically values of a and b is getting added. Okay, those two values are overwritten, and new top of the stack will become the result of addition of a plus b. Okay, so now at the top of the stack, what is stored? The top, at the top of the stack we are storing the result of addition of a plus b. Then what we'll do, we'll give a command push c. So what it will do, it will push c to the top of the stack, and the result of addition of a plus b will be at t minus 1 location. Okay, so please try to understand very carefully how this program is being executed. Okay, so top of the stack is now c, and top of stack minus 1 is the result of addition of a plus b. Okay, then again we are giving push d. So when we are giving the command push d, what is happening is the new top of stack becomes the d, means the new top of stack location is having the value d. Then what is top of stack minus 1? C, and top of stack minus 2 is a plus b, the result of addition of a plus b. So this thing needs to be very clear, that top of stack is d, top of stack minus 1 is c, and top of stack minus 2 is a plus b. Okay, then we will give a command add. When we are giving a command add, as you all know, in zero address instruction format, the two values are always fetched from top of the stack and top of stack minus 1. So top of stack, as you can see, is D, and top of stack minus 1 is C. So the two values will be fetched, C and D, to the arithmetic and logic unit. The addition operation will be performed, and the result of addition of C plus D will be stored at the top of the stack. So now at the top of the stack, what is stored? The result of addition of C plus D, and T minus 1, top of stack minus 1, the result of addition of a plus b. Now we are giving the command multiply. Okay, so just like add instruction, whenever we are giving the command multiply, then also the two values will be fetched from top of stack and top of stack minus 1. So let us see, the top of stack is having c plus d, the result of addition of c plus d, and top of stack minus 1 is having the result of addition of a plus b. So c plus d will be multiplied by a plus b, that is now new top of stack. Then this is something called as pop x. What is the meaning of pop? We are reading the data, or we are taking the data from the stack. We are moving the data from the top of a stack to some other memory location which is specified by the x. So the top of the stack, whatever value was stored or saved at the top of the stack, this will be stored at a new memory location which is specified in the instruction, and we are referring it by the word x. Okay, so now something you need to understand. Let us see, in three address instruction, the same equation can be executed by using three instructions only. In two address, we were requiring 6. In one address, we were requiring 7. And in zero address, we were requiring 8. Okay, so now one may ask that what is the use of different instruction formats? Means it is clearly visible that if we are having three address instruction format, then we are requiring the least number of instructions or least number of steps to execute the given equation. Okay, so then why there should be two address instructions, or why there should be one address instructions, or even zero address instructions? So the answer to this question is that depending upon the type of instructions or structure of machine, there are basically two major philosophies. Okay, one is called as risk philosophy and another is called as CISC philosophy. Risk philosophy specifies or stands for reduced instruction set computer. Okay, and CISC stands for complex instruction set computer. Okay, so basically risk philosophy, what does the risk philosophy specifies? That the basic operations only is supported by risk computers. The complex equations are not supported by the risk computers. So what risk computer basically tries to say is there should be only basic instructions that a computer should be execute. Basic instructions like load, add, store, etc., push, add. Okay, so these are the basic operations. Risk machine only supports the basic operations. It does not support very complex instruction or complex operations. Okay, so basically what does a risk philosophy means? That these basic instruction or operation should be carried out in one clock cycle, and the speed is achieved by the help of pipelining. Okay, so whenever we are going to study pipelining, these things we need to understand, that the simple instructions can be executed in one clock cycle. Okay, we do not require very complex setup or complex mechanism for executing the simple instructions. So even though the number of steps is more in risk philosophy, okay, but since these instructions or these steps are carried out parallelly by using pipelining, so we can achieve a very fast execution of programs. Okay, as opposed to this, There is a CISC philosophy which specifies that okay, the computer should support complex instructions, means the user should not be given the load to write a program which is very lengthy, which must be having thousands and millions of lines of instructions, but the user must be able to write very complex mathematical equations. Now it is not the job of user to worry about the complexity of the program or complexity of instructions. It is the job of the compiler and the machine to convert those complex instructions and programs into simpler programs and then try to execute it. Okay, so basically user will write very complex equation and very complex instructions, and then these complex instructions and a program will be converted into basic operations, just as we are seeing in one address or zero address, and then they will be executed. So actually the time required to execute one instruction in this philosophy will be very high as compared to the time required to execute a single instruction. If we are considering load a as a single instruction, so time required to execute one single instruction in 0 or 1 address will be very very less as compared to time required to execute this particular instruction which is having add a comma b comma r1. Okay, but what is the difference in 3 address instruction format or complex instruction set computers? The number of instructions will be less, but time required for executing per instruction will be very very high. And what is happening in risk computers? The number of instructions will be high, but the time required to execute one instruction is low. Okay, this is the difference between risk and CISC philosophy, and that is why we are having so many instruction formats, that depending upon the requirement of the user, we should not restrict the user to any one particular format. All the philosophies have their own advantages and disadvantages, so whatever is required by the user, he must be able to get that particular thing. Okay, so these are instruction formats. I hope these instruction formats are very 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 clear to each and every one of you, because these are very important concepts that you must understand if you are trying to learn computer architecture and organization. Okay, then there is something called as addressing mode. This is another very important concept when we are studying the computer architecture and organization. There are so many different type of addressing modes which are supported by the machines. Why do we need addressing mode first? Okay, so let us try to understand the definition of addressing mode. What do we mean by addressing mode? Addressing mode is the different ways in which the location of an operand is specified in an instruction is called as addressing mode. What are we trying to say? That whenever instruction is fetched into the processor. Okay, now we are very clear on this thing, that what is the processor do? It try to decode that particular instruction. Okay, while decoding, it is trying to actually finding out that what is the opcode and what is the operand. Okay, so opcode is quite easy to understand, that it is the simple instruction that needs to be performed. Either it is addition, subtraction, multiplication, move, store, push, pop, read, write. These are the operations. These are the opcodes. Okay, so these are the operations that are specified in the instruction. Okay, but the complex thing is to understand that where are the values of variables which are specified in the instruction. How does the processor know that a and B are memory locations and they are not the address of general purpose registers? So basically, it is very important because the computer or the processor actually has to go to that particular physical location and fetch the data from that particular location. Okay, so there must be some rules which specifies or which tells the processor that whatever operand are specified, whatever value variables are specified in the instruction, what is the exact meaning of that variable, so that processor can understand that particular instruction and fetch the values of variables into the processor. Okay, so these things are made possible with the help of addressing modes. Now let us try to understand one by one that what are the various addressing modes, or what are the various common addressing modes that are supported by most of the machines. Okay. There are so many different type of addressing modes. Okay, now there are two modes in which the values are directly specified in the instruction only. So basically, as you can see from this particular slide, that total overall there are 10 different addressing modes. Okay, the but out of these 10 addressing modes, most of the addressing modes, what they do, they modify the value of the they modify the values which are present or which are specified in the instruction. How do they modify the values, that thing will be clear when we are going to see the example. But these two addressing modes are such that no values are modified at any location, either at the memory location or at the register. The reason is the values that are required for performing the operation are explicitly specified in the instruction itself. Okay, so that is why no uh, values in the memory or register is getting changed from these two addressing modes. Let us see. First is implied addressing mode. What do we mean by implied addressing mode? In this mode, operands are specified implicitly in the definition of instruction. For example, zero address instruction in stack organizes the CPU. The operation type instruction do not need an address field. The instruction add. Okay, so what is happening, as we have seen previously in add, we are not specifying any address in the we are not specifying any address here. So by default, we know that whenever we are giving the add command, the two data will be fetched from the top of the stack. They are not present in any memory or in any general purpose register. So data will be fetched from stack, and the result of addition will be also specified or modified or stored at the top of the stack. Okay, then second is immediate addressing mode. What do we mean by immediate addressing mode? In immediate addressing mode, uh, the data which needs to be operated upon is specified in the instruction itself. For example, consider move r hash 20. So basically, what this instruction is specifying, that you need to move a value 20, a numerical value 20, into the general purpose register r. Okay, so a value 20 will be moved where? In the general purpose register R. The register will be initialized with a constant value 20. Now this hash is very important. Whenever we specify hash in front of any numeric value, then it specifies that this particular value is a constant. Okay, so here one thing is very important that you must understand, that previously I told you that normally the instruction is read as opcode source comma destination. Okay, so always uh, source comma destination. So what we are trying to say here is that this 20 can be moved to r. Okay, the vice versa is not possible, because 20 is a constant value, so we cannot store the contents of r into the constant value 20. It can be done only in this particular way possible. The constant value 20 can be moved to the source r. Okay, so the value which needs to be operated upon, okay, that will be given specifically in the instruction. Just like here, hash 20 is given in the instruction. So this is the particular value. We do not need to go to any register, or we do not have to go to any particular memory location to find that which value needs to be transferred to memory location r. It is specifically mentioned here only that you need to initialize the memory register r with a constant value 20. Okay, this is known as immediate addressing mode, where the value upon which the action is to be taken, upon which the operation has to be performed, is given in the instruction itself. You do not have to go to any memory location or any particular register and fetch the value from there. Okay, understand this thing. What do we mean by immediate addressing mode? That the value upon which the operation is to be performed is given in the instruction itself. You do not have to go to any particular memory location or any particular register to fetch the value. Okay, directly the value is given in the instruction itself. This is called as immediate addressing mode. Third thing is register addressing mode. Okay, if you can remember the diagram that we have studied earlier, in the register addressing mode, uh, we have studied that there are n general purpose registers which are present within the CPU itself, and I have also told you that these general purpose registers can be used by the programmer in his program. Okay, so it is possible that you can write a command which looks like this: move r1 comma r2, or you can write a command add r1 comma r2, or you can write a command sub r1 comma r2. So when you are giving a command move r1 comma r2, so basically what is happening? Okay, so as you can remember, this is source and r2 is destination, and move is the opcode. So move, basically what do we mean by move command? To move the value. Okay, which value? The value of r1, where? To the register r2. That is what is specified here. Opcode. Opcode is specifying the operation. What operation we need to perform? We need to perform the move operation. Okay, then where are the two values, or what needs to be moved? So the value of r1, the value which is present in the register r1, it needs to be moved. Where? Destination. It needs to be moved in the register r2. So from the r1 register, whatever value is present in the r1 register, it will be stored in the r2 register. Okay, suppose we would have written the command add r1 comma r2. So what would have happened? What would be the opcode? Opcode would have been addition. Okay, so we would have performed addition operation. Okay, now next thing is, for performing the addition operation you need two variables. Where are those two variables? First variable or first value is present in the r1 register. Okay, so first value will be fetched from r1 register. That value will be transferred to the arithmetic and logic unit. Okay, where is the second value? Second value is present in the R2 register. So value from the R2 register will be transferred to the arithmetic and logic unit. Okay, now both the values are present in the arithmetic and logic unit. So arithmetic and logic unit will perform the addition operation. After performing the addition operation, where is the result of R1 plus R2 is going to be stored? So again, opcode source comma destination. What is the destination? R2 register. So from arithmetic and logic unit, the result of addition of R1 and R2 would have been moved to R2 register. Okay, so result is stored in R2 register. This is known as register direct addressing mode. What do we mean by direct mode? In the direct addressing mode, whatever the names of registers are specified, they are directly holding the values. Okay, if the names specified in the instruction or the address specified in the instruction is holding the values directly, then it is known as direct addressing mode. Okay, there are something called as indirect addressing mode also, which we are going to see next. Okay, this is interesting. This is register indirect addressing mode. Okay, indirect addressing modes are basically utilized whenever we are using the concept of pointers. Okay, so what is the difference between direct addressing mode and indirect addressing mode? In the direct addressing mode, the value was present directly. The content of the registers were the values, okay, which needs to be operated upon. But in indirect addressing mode, the content of the register specified in the instruction will not be values, it will be the address. This is the difference between direct and indirect addressing mode. Let us try to understand it through the example which is specified in the instruction. What is the instruction specified in the instruction? It is given move a comma R. Okay, now what is the difference you can see in both the instructions? Here we are not covered the name in parenthesis, and you can see here the register R is specifically written within the parenthesis. So this parenthesis tells the processor that this is an example of indirect addressing mode. What do we mean by indirect addressing mode? That the content of register R1 is not the value. In fact, it is the address of value from which the data is to be fetched. Let us see it by an example. Okay, so move is the opcode. We are almost very clear on this thing that move is the opcode. Then source comma destination. Okay, so what we need to do, we need to move the values of a where to the address which is stored in the register R. See this thing, register name A. So here A is the memory location where one value is stored. From this particular memory location, we need to store or move this value where to the address which is specified in the register R. Okay, so basically what is the content of register R? It is the address of a memory. Okay, so first we will go to register R, then we will fetch the address. To that address we are going to store the value which was stored in A. Okay, this is indirect addressing mode. If it was a direct addressing mode and we would not have written R in parentheses, then what would have happened? The value which was present in A would have been stored in the memory register R. But since it is an indirect addressing mode, the value which was stored in the memory location A is not stored in the register R. In fact, from register R, we have obtained another address of a memory location, and at this particular memory location, we are going to store the contents of memory location A. Okay, so this is the fourth addressing mode, which is known as register indirect addressing mode. It is very important addressing mode because these addressing modes are used in pointers, and we know, I mean, since you have already studied C and so many programming languages, so you know pointers are very important concept. Pointers are used very heavily in almost all of the programming languages. Okay, so to implement the pointers we must understand the concept of indirect addressing mode. Clear? Okay, we'll move forward. Then we have something called as auto increment and auto decrement addressing, auto increment and auto decrement addressing mode. Okay, what do we mean by auto increment and auto decrement addressing mode? Suppose you need to perform the addition of 10 values. Okay, so if you need to perform the addition of 10 values, you need to fetch 10 values one by one. Okay, now if these values are stored at the successive memory locations, okay, then you can use the auto increment or auto decrement addressing mode. Let us try to understand this by using an example. Okay, so what example is given here? Add R1 comma R2. Okay, so now understand this thing, that R2, and we have specified plus sign here. So what do we mean by plus sign? That it is an example of auto increment addressing mode. Okay, if we would have written there minus sign, that then it would have been an example of auto decrement addressing mode. Okay, so let us try to understand what is specified in this particular instruction, add R1 comma R2. So one thing is very clear here, that since R2 is written in the parenthesis, then R2 is not holding the value. In fact, R2 is holding the address. Okay, so what do we need to do? What is specified in the opcode? Opcode is specifying that we need to perform the addition operation. Okay, so okay, we are performing the addition operation. Now next thing is, for addition we require two variables. Okay, that is also fine. One variable is present in R1, Okay, so R1 is there. Next is R2, but R2 is specified in the parenthesis. That means that the value, second value which is required for addition operation is not present in the R2. In fact, the value which is required for addition, its address is present in the R2. So we'll go to R2 register. From R2 register we will fetch one value, and that value is the address where the particular data is stored. We'll go to that particular memory location and we'll fetch the data. Okay, so now these two values will be added, but we have specified here plus. So what will happen, the result of this addition is again stored in the R2, and this value of R2 register will be saved, will be based used as the base address. And for adding the next number, means for adding the third number, we will increment the value by 1. So suppose the value of R2 register is 1002. Okay, so when we are performing this operation for the first time, the content of register R1 is added to the content of memory location 102. Now next time the content of R2 register is automatically incremented by 1. So now next time, what will be the content of R2? 103. So 103 location we will fetch one value. That value will be added to what? The result of addition of R1 and R2. Okay. Now again R2 will be incremented by 1. So next memory location would be 104. Now this the data from memory location 104 will be added to the result of addition of R1 plus R2 plus R3. So okay, in this way, if we are requiring to execute a loop 10 times, so this is how the loop can be implemented. Okay, so we are basically using the auto increment or auto decrement mode if we are trying to implement a loop in any programming language. Okay, now there is something called as direct addressing mode. We have seen the direct addressing mode, register direct addressing mode here. Okay, then this thing is called as memory, direct memory addressing mode. Okay, or simply direct addressing mode. What do we mean by direct addressing mode? That operand is given directly in the instruction, and basically that operand when added to the content of a register will give you the effective address. Okay, so understand this thing. What is the example given here? Add r comma 2000. Okay, so r is the register where one value is present. Okay, now 2000 is the address. So basically what we need to do is we need to add the contents of r plus the 2000 is address. So this particular address is the effective address where our second value is stored. We need to go to this particular address and fetch the value from there, and then the addition operation can be performed. Okay, so this is called as direct addressing mode. Indirect addressing mode is same as register indirect addressing mode. Here when we were writing the name of the register in parenthesis, it was register indirect addressing mode. If we are writing the name of the memory location in parenthesis, then it is called as memory indirect addressing mode. Okay, so both direct and indirect addressing mode can be register and memory. Okay, so there can be direct addressing, register direct addressing mode, register indirect addressing mode. There can be memory direct addressing mode, and there can be memory indirect addressing mode. Okay, and relative addressing mode is not that important. Index addressing mode, index addressing mode, there is a base register present. Okay, and from that base register there is a constant value specified, so we keep adding that constant value to the base register to obtain the value of next addressing mode. We'll directly go to the example. Okay, so suppose you have been given an instruction. Okay, from where opcode is specified and base register address is 1000. Okay, so to the base register address you will keep adding the values from the base register to the value specified in the instruction, and that is how you will obtain the address of the next instruction. Quite similar to uh, what we have studied in the auto increment and auto decrement addressing mode. Okay, now these are some of the questions that have been asked in the gate uh, that are related to addressing modes. Okay, so first question is, match each of the high level language statements given on the left hand side with the most natural addressing mode from those listed on the right hand side. Okay, so what do we need to specify? That here an instruction is given. Okay, first instruction is a1 is equal to bj. Okay, what is second instruction? While star a plus plus. What is the third instruction? Int temp equal to star x. So these are the three instructions that are specified on the left hand side of the instruction. Okay, and then the name of the addressing mode is specified on the right hand side. First is indirect addressing mode, second is indexed addressing mode, and third is auto increment addressing mode. Okay, so basically you need to match the pair. That first instruction a1 equal to bj, this is an example of which of the particular addressing mode. While star a plus plus, this is an example of which of the addressing mode. Third is int temp equal to star x, this is an example of which particular addressing mode. Okay, so these thing you need to match this thing, and you need to find out that from the four options given below here, which are the which option specifies the correct matching. Okay, so what is the option? 1c 2b 3a, 1a 2c 3b, 1b 2c 3a, and 1a 2b and 2 1a 2b and 3c. Okay, so the correct answer here is option number C. What is option number C? Okay, first instruction which is given here, A1 equal to BJ. This is an example of indexed addressing mode. Okay, so 1 is matched with B. Second is 2, while star A plus plus. Okay, this is an example of auto increment addressing mode. How do we know that it is an example of auto increment addressing mode? You can see here the plus plus sign which is written after a plus plus, means whatever the contents of register a, it needs to be auto increment, it needs to be incremented. Plus plus sign is an plus plus is the sign of increment. Okay, so from here we can understand that it is the auto increment addressing mode. Also we have studied that auto increment addressing mode is used where? It is used while we are trying to implement the loop. Okay, so here while is also specified, so it is quite clear that we are trying to implement a loop here, and plus plus sign is also an indication that it is an example of auto increment addressing mode. So 2 is definitely an example of auto increment addressing mode. Okay, now see here, third example, int temp equal to star x. Okay, so we means what we are trying to implement here? We are trying to implement here pointer. Okay, and if we have studied pointer, we all know that what is the pointer? It holds the location, it holds the address of a value. Okay, so here the x is, when we are writing such statements, int temp equal to star x. Now what we are trying to specify here is that x is not a variable which is holding a value. In fact, x is the address, x is holding the address where the value will be present. Okay, so this is an example, or this is an example of pointers. We are trying to implement pointers here. Okay, and if you remember what we have studied, that indirect addressing mode is used to implement the pointers. So it is also quite clear that int temp equal to star x is an example of indirect addressing mode. So third is matched with a, 2 is definitely matched with C. So 2 and C are matched. 3 and A are matched. Okay. So by default, first and B, first will be an example of index addressing mode. So most correct option here is option number C. 1 is matched with B. 2 is matched with C, and third is matched with A. Okay, this is what we have studied in the addressing modes in the previous slides. Okay, now let us see another example. What is the question asked here? In the absolute addressing mode, the operand is inside the instruction, first option. The address of operand is inside the instruction. The register containing the address of the operand is specified inside the instruction, and the location of operand is implicit. Okay, so absolute addressing mode. Okay, absolute addressing mode is same as immediate addressing mode. This thing you need to understand, that in some books the immediate addressing mode is also referred by the name of absolute addressing mode. Okay, and what we have studied in immediate addressing mode, that the operand is implicitly specified in the instruction itself, means you do not have to go and find the value of operand to some register or some memory location. The values are implicitly given in the instruction itself. Therefore, the correct option for question number 2 is option number D. The location of the operand is implicit. It is given in the instruction itself. Okay. Then third and last question. Which of the following addressing modes are suitable for program relocation at a runtime? Absolute addressing mode, base addressing mode, relative addressing mode, and indirect addressing mode. Okay, so now we need to apply some concepts also. The questions in gate will not be direct and very easy. Okay, so what do we mean by program relocation at the runtime? So program relocation at runtime means we are copying a block of a program. Suppose a program is of 10 lines, so we are copying that program from one memory location, and we are storing that program at some other memory location, and then we need to run that program. Okay, so in program, whenever we store a program at any particular memory location, the lines of program are stored at the successive locations. Means if line number 1 of program is stored at location number 1, then line number 2 of program will be stored at line number 2, or address number 2. Line number 3 will be stored at line number 3 will be stored at location 3, and so on. So line number 1 is stored at 1, line number 2 is stored at 2, line number 3 is stored at 3, and so on. Okay, so if we need to obtain the address of all the 10 lines of program, what do we know? What do we need to know? We need to know the address of starting. Okay, we need to know the address of starting or first line of the program, and to that base address, if we keep adding, or if we keep incrementing that base address by 1, we will obtain the address of second line. For example, if we somehow able to fetch the address of line number 1, which is address number 1. Okay, so and to this, if we keep on adding 1, so we will keep on getting the address of next instruction. Okay, so what is the options given here? What are the addressing modes that will be required for this particular thing? First option is 1 and 4. What is 1 and 4? Absolute addressing and indirect addressing. Second is option number B is 1 and 2, absolute and base. Second is C is 2 and 3, that is base and relative. And D is 1, 2, and 4, means absolute, base, and indirect addressing mode. So one thing we are very clear here is that we do not need the indirect addressing mode here, because we are not using any pointers. Okay, so indirect addressing mode will not be required here. Okay, base address is required. It is quite understandable that without base address we cannot do this thing, because we simply need to find the base address and then keep on incrementing the address. Okay, in the absolute addressing mode, the value of the operand is directly given, therefore absolute addressing mode is also not required. So then what are the two addresses that remains? Base is required for sure, and along with base we need to have one more addressing mode. Okay, but absolute is not required and indirect is not required. So what that leaves us with? only two options, base and relative, because all the options have given almost at least two addressing modes. Okay, so what should be the correct answer here? The correct answer should be option number C, 2 and 3. We are having, if we can obtain the base address at the runtime, and to that base address, if we can auto increment or add something to the base address, we will keep on getting the address of the next instruction. So that means a combination of base addressing and relative addressing, we can implement the thing that is asked in the question. Hence C is the correct option. Okay, so these are some of the examples that I have tried to give you based on what I have taught you. In tomorrow's lecture we are going to cover memory. Means what is the memory, what is the RAM design, what are the memory hierarchy, what is cache memory, and all the basic concepts that are related to memory. This was the concepts related to memory architecture, instruction formats, and addressing modes. I hope you must have find this lecture useful, and you must be able to score good marks if questions related to these topics are asked in the gate questions. Thank you very much.